in this lecture we are going to continue our discussions on particle kinetics. We will look at some problems in which we will apply Newton's laws of motion and solve them. The first problem that we have today is this particle resting on a rotating conical dish. The problem statement says the small object is placed on the inner surface of a conical dish at a radius shown. If the coefficient of static friction between the object and the conical surface is 0.3, for what range of angular velocities omega about the vertical axis will the block remain on the dish without slipping? Assume that speed changes are made slowly so that any angular acceleration may be neglected. This is a problem from the book of Merriam and Craig, Dynamics. From the figure you can see that this conical dish, how it is rotating and where the object is placed, and this angle is also specified. The whole system is in a uniform gravitational field. First step is to set up the coordinate system, and you notice the way I have set the coordinate system, I have taken x axis along the plane upwards, z axis perpendicular to the plane upwards, and y axis therefore must be into the plane, perpendicular to the plane of the screen and into the plane. Once we have this coordinate system fixed, then we draw the free body diagram. This is the small block whose free body diagram we have to draw. The first thing that you notice is the weight which is acting vertically downwards. Then there is this normal reaction from the inclined surface, the surface of the dish, which is acting perpendicular to the surface, and then you also see Fx, which is the friction force between the block and the dish along the x axis direction. Now, because this surface is two dimensional, therefore, there will be in general two forces of friction. One is this Fx, which you can see on the free body diagram, other is Fy, which I have indicated by the convention that we normally use to show a vector into the plane of the screen, perpendicular and into the plane of the screen. Fy is unknown and is into the plane of the screen. Please note that this is the general free body diagram of this block on the dish. We do not know a priori which friction forces will apply in which direction, and magnitude is definitely out of question. With this free body diagram, next we are going to look at the kinematics of the problem. There is one more thing I should mention here in relation to the free body diagram. You must notice this very carefully. I have not shown any pseudo forces. We will not use pseudo forces. Pseudo forces are out of the realm of Newtonian dynamics, and I ask you to refrain from using this concept pseudo forces. Then we look at the kinematics. Acceleration of this block, which I call A, I am expressing in terms of acceleration of this point B, which is on the axis of rotation. As you can see on the figure, I have marked it. An observer at B then notices the acceleration of block A and writes acceleration of block A is acceleration of the observer plus A rel plus alpha cross B A plus omega cross B A plus 2 omega cross V rel. Now, this is the our most general expression of acceleration. Here, first thing you notice that if the block is not slipping on the surface, then block is sticking to the dish, and therefore, the block is as if a part of the dish. Therefore, A and B are parts of the same rigid body. Therefore, A rel vanishes and V rel vanishes. The point B is on the axis, therefore, its acceleration is 0, it is not moving. The dish is not accelerating, so its angular acceleration is 0, therefore, alpha is 0. What we are left with therefore is only this omega cross BA, this term, where omega is the angular velocity of the frame. Now, I have just represented these vectors in the coordinate system that I am using. Omega vector, the angular velocity vector, can be represented like this: the magnitude, which is omega, times unit vector, and you can easily find out the unit vector of the vertical direction. This angle is given as 30 degree, therefore, this is 30 degree, this angle is 30 degree. The unit vector in that direction therefore is sine 30 degree I cap plus cosine 30 degree k cap, and omega cross the vector B A. Now, vector B A is again the magnitude of B A times the unit vector direction, which is I cap. B A is along x axis, and this you can very easily find. This is 0.2 given, this is 0.2 meter, and this is 30 degree. Therefore, B A is 0.2 by cosine 30 degree, and it is in I cap direction, and this simplifies to this expression. Once the kinematics is set, we can now go over to the equation of motion. Mass times acceleration of A is equal to sum of all forces acting on it, and all these forces are very clearly shown in the free body diagram. So, what we have to do is only represent these forces in the coordinate system chosen. The force of friction, there is an x component along I cap, y component along j cap, f x I cap plus f y j cap. Weight is vertically downwards, this is mg times a unit vector which is vertically downwards, plus normal reaction is perpendicular to the plane which is along z, and therefore, it is n times k cap. Now, we look at the components. Here the first thing we look at is the I cap component. This is the I cap component. Mass times acceleration in I cap, acceleration in I cap is 0.2 omega square times minus cosine 30 degree. So, this and mass is sitting here, and that is equal to all the forces in the I cap direction. These are the two forces in the I cap direction. Therefore, we have these two terms on the right hand side. Now, the j cap, there is no j cap in the acceleration, therefore, the left hand side is 0. Right hand side j cap, I have only f y, therefore, 0 must be equal to f y. So, f y is 0. So, my equation of motion will tell me this. I will not assume or choose a priori. Then comes the k cap equation. We have in the k cap direction here in the acceleration a term, mass times that term must be equal to all forces in the k cap direction. K cap direction I have these two forces. So, that is the k cap equation. Now, from these equations I must now use the no slipping condition. What is the no slipping condition? No slipping condition will be the net magnitude of the friction force divided by the normal force at the interface should be less than the static coefficient of friction. Now, in this case it so happens that f y is 0, magnitude otherwise would have meant magnitude of the net friction force would have been f x square plus f y square under root. because Fy is 0 as it turns out, therefore, it is only the magnitude of Fx. Now, this condition must be satisfied for no slip. I have just solved these terms. For example, Fx I have solved from the first equation, n I have solved from the second equation, third equation, the k cap equation, and I have taken this ratio. Only thing I have to take this magnitude of Fx, and that should be less than 0.3, which is the coefficient of static friction. This is our condition of no slip. The denominator, you will notice, is positive. Therefore, I can take it to the right hand side without change of the inequality, and the mod value I will change by the plus or minus. And if you solve this inequality, you will obtain omega must lie between 3.4 radian per second and 7.2 radian per second. It should be interesting to note that omega should not be 0 or less than 3.4 radian per second, then the object will slip, and definitely it will slip inwards towards the center. So, that completes this problem. Next problem is about a small cylinder which is being projected onto a moving belt, a long moving belt. I have shown in the figure a part of the belt, and I have shown the movement direction and the velocity. The problem statement says a small cylinder is projected with a speed u from an adjoining platform perpendicularly onto a long horizontal belt moving at a constant speed v, capital V. The coefficient of kinetic friction between the block and the belt is mu k. A part of the problem asks you to calculate the time taken by the cylindrical block or particle to stop on the belt, because there is friction. If you project that cylinder, it will start moving initially on the belt, but because of friction it will come to a stop somewhere. We have to calculate the time taken by the cylinder to stop on the belt, and the B part of the problem asks us to determine the path of the particle as seen by a ground based observer and an observer on the belt. So, part B has two parts actually. One part, the first part is to determine the path as seen by a ground based observer, the observer who has possibly pushed the cylinder onto the belt, and the path as observed by an observer who might be moving with the belt, sitting on the belt and moving with it. For example, if this cylinder were freshly painted, then it would leave a trail on the belt. We would like to find out what is the paint mark, how does it look on the belt. First thing is to set up the coordinate system. I have taken the coordinate system x, y, z fixed on the ground, non-moving. This x, y, z is therefore fixed to the platform from where the particle is pushed, and the particle is initially at time t equal to 0, it is at the origin of this frame. Now, this particle, you can imagine, when it is pushed, I am pushing it along the y axis direction as shown in the figure, but because the belt is moving and there is friction, the particle is going to change its course, and this red dashed line indicates, roughly indicates how the particle should be moving. And the velocity of the particle as seen by the observer on the platform, fixed platform, is tangent to this path. This is the velocity of the particle that the stationary observer will see, and this velocity is tangent to that path the particle will follow. Now, we come to the free body diagram of this cylindrical particle. Weight mg is acting vertically downwards, normal reaction from the belt is acting vertically upwards, and the friction force, which in this case I definitely know is mu k times n, that is why I have written it, because it is sliding. As long as it is sliding, it is mu k times n. Now, what is the direction of the friction force? Now, that is a tricky question. That will not be opposite to V c, the velocity of the particle as seen by the fixed observer, platform fixed observer. Friction force always acts against the relative motion, remember, it always opposes the relative motion. Now, because the belt is moving and the block or the cylinder is moving initially, so it is a relative motion against which the friction force will act. So, we have to determine that. The kinematics. If I say that in this coordinate system that I have shown, at any point of time the coordinates of the cylinder is x, y, therefore, the velocity vector I can write as x dot I cap plus y dot j cap, because I and j are not changing directions, they are not changing direction. Therefore, the position vector is x I cap plus y j cap and velocity is x dot I cap plus y dot j cap, as it happens in a Cartesian coordinate system fixed with distant stars. Now, velocity of the belt is v capital V I cap in this frame. Therefore, the relative velocity between the cylinder and the block, which I have written as V c with respect to B, is the difference V c minus V b. This must be equal to V c minus V b. And that happens to be x dot minus capital V I cap plus y dot j cap. Now, the force of friction, whose magnitude is mu k times n, acts opposite to this direction of the relative sliding vector. Now, direction of relative sliding vector means it is the unit vector of the relative velocity, and unit vector of this relative velocity, how will you find out? That can be found out easily by, therefore, this V c with respect to B unit vector is nothing but the vector itself V c relative to B divided by the magnitude, and the magnitude is x dot minus V whole square plus y dot square. That gives us a unit vector. Now, once the kinematics is set, we move over to the equation of motion. Mass times acceleration of the cylinder is equal to the net force acting on the cylinder. Now, acceleration of the cylinder is nothing but the derivative of velocity, and I cap and j cap are fixed unit vectors. Therefore, acceleration is x double dot I cap plus y double dot j cap, and mass times that must be equal to the net force acting. Now, we have normal reaction in the k cap direction, weight in the minus k cap direction vertically downwards, and this force of friction which I have written out. If you now take the components, the I cap component will give you m x double dot as this. Here I have used that expression of the unit vector of in the relative velocity direction. Similarly, you can find out the j cap equation, and the k cap equation is nothing but balance of force, because there is no acceleration in the vertical direction. What it tells us is the normal reaction is nothing but the weight of the block. Okay. So, we proceed with these equations of motion. So, x and y, these are the two directions in which we have to solve. Now, these are two second order ordinary differential equations of, therefore, we require 4 initial conditions. At time t equal to 0, it started with the at the origin of the coordinate system, therefore, x and y must be 0, and the velocities, the x velocity was 0, but y velocity was u. This was the velocity that the person from the platform launched this particle onto the belt with. Now I should be able to solve, but you see these equations look formidable. X double dot is in, I mean it involves x dot, it involves y dot, and in a very complicated manner. It looks almost like unsolvable, but there is a step that if you take, this becomes very simple, and that step is first writing this as dx dot dt and this as dy dot dt, and then taking the ratio dx dot by dy dot, you take the ratio of these two accelerations, we get dx dot by dy dot, and what is interesting is this part is common in both, and also the negative sign. Therefore, we are left with only this simple expression on the right hand side, x dot minus v by y dot, and this can be solved. If you integrate this once, you will get a constant of integration which I have written as c. This integration is straightforward, and using the initial conditions you can find that this c, the constant of integration, is minus capital V by u. Now, if you substitute back this expression, use this expression in our equations of motion in 1, then you will arrive at these two simplified equations. This you can very easily check. You have to just use this x dot minus v is minus capital V by u y dot everywhere, here, 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 and then you will get x double dot and y double dot surprisingly as constants. So, these are finally my simplified equations of motion, which I need to integrate, which is very straightforward. I integrate and use the initial conditions, always integrate and use the initial conditions. This gives me the velocity, and you can note that t equal to 0, at time t equal to 0, x dot is 0, y dot is u. Now, we have to find out the stopping time it takes for the particle to stop on the belt. When do we say that the particle has stopped on the belt? When the y velocity is 0, either y velocity is 0 or x velocity as seen by the observer on the ground, on the platform. Observer sees that the particle is now moving with the belt at the same speed as capital V. Therefore, you can use either of these two conditions to find out the time to stop, and that turns out to be square root of v square plus u square by mu k times g. Therefore, this solution is valid till the particle is moving. That means time is less than equal to the stopping time. Till then, this is the path. I have integrated once again, as you can see. This is the change of coordinates with time as seen by the platform fixed observer as long as the particle is moving on the belt. I can find out the path. Now, the question was find out the path as seen by the platform fixed observer. To find out the path, what I have done is I have just eliminated time between the two. How do I do that? I solve for time from, let us say, this and substitute here, and I get y as a function of x, and you can see that it varies as square root of x and square root of x. So, there is a quadratic dependence of x on y, and this path is valid as long as time is less than equal to the stopping time. Okay. So, this is our path as observed by the platform fixed observer. This is the belt and that was the approximate path. So, this must be the equation of that path in the x y coordinates fixed to the platform, fixed to the earth, not moving with the belt. At certain point, the Ts, the particle starts sticking, it sticks to the belt, and then its velocity will be just capital V, it moves with the belt. This is the start of the sticking phase. At time t equal to Ts, let us find out where the particle has reached. Here what I have done is, in the time expression I have substituted time as Ts. So, here t is equals to Ts, and I have found out what is the x and y coordinates of the cylinder. Now, once I have them, I can now find out the position of the particle, subsequent position of the particle starting from here. It is sticking to the belt, therefore, its x coordinate must now change as Vt, because its velocity of henceforth this velocity is only V, and it starts with this initial condition x equal to whatever it reaches at Ts, and similarly for y. Now, you will notice that x is a function of t, because the particle is moving with the belt at a constant speed capital V, but y is frozen, y does not change with time. Now, for an observer on the belt, this was the second part of part B of the problem. For the observer on the belt, what will be the motion of the particle that observer will see? Or if this cylinder were painted, what paint mark would it leave on the belt? Let us start with that relative velocity. Relative velocity, why we need to go to relative velocity? Because that will tell us the velocity as seen, or the motion as seen by the observer on the belt, and this was the expression we found out by integration, and this is valid till it is sliding. Now, I imagine another coordinate system which is now moving with the belt, but co-oriented with that x, y, z on the platform. That means, this I cap and j cap directions are same as this I cap prime, what I have shown here. I cap prime is on the belt, j cap prime is on the belt, and they are in the same directions as I cap and j cap. Remember, unit vectors always indicate directions. Therefore, the x y coordinates for the observer on the belt is co-directed with x y of the observer on the platform, and therefore, the coordinates of the particle, which is capital X and capital Y for the belt observer, can be represented. So, velocity can be represented like this, and this relative velocity is same as this relative velocity which we have found out, which I obtained by substituting this here. These two must be the same, and I cap prime and I cap are same, j cap prime and j cap are same. Therefore, I just divide dy, so y dot by x dot, this is nothing but y dot by x dot, which I can write as dy by dx is minus of u by v, again a constant. Therefore, y must be minus u by v, capital V times x. This tells us surprisingly that the coordinates of the cylinder as seen by the belt based observer is a straight line with constant slope. This has a constant slope, it is a line, right. Therefore, if this cylinder were painted, it would leave a line on the belt. Therefore, the path on the belt of the cylinder is a straight line, and as long as, of course, time is less than the stopping time. This is the mark that will be left by the paint. At the point of sticking, which occurs at t equal to Ts, I exactly know the coordinates, which I can find out. This is straightforward algebra, I will leave it to you. So, to summarize, we have discussed a couple of problems involving this 4 steps in Newtonian dynamics. With that, I will close this lecture.